All right. Hello, everyone, and welcome to Lecture 6 of the Building Planets series, Small Worlds, Asteroids, Comets, and the NASA Psyche mission. I'm really excited about this one in particular. It's a great distraction and has some amazing facts in it. So first, let's review the last lecture, which was about the early Earth. Hang on a moment. There we go. Okay. The last time we were talking about Earth from about 4.5 to about 3.8 billion years ago. And around 4.5 billion years ago was the moon-forming giant impact on the Earth, which melted the Earth into a magma ocean. Very little material exists on the Earth before 4 billion years that is dated to before 4 billion years. Thus, these Jack Hill's zircons are key evidence for conditions on the early Earth. The zircons and then models for magma ocean solidification both show that the Earth was cool and clement before 4.4 billion years ago, despite the fact that there was a high impactor flux up through the late heavy bombardment. So this time, we're talking about the small worlds in our solar system, and we're talking about the small worlds that exist today, that exist now. Why do the big planets get all the attention? Our solar system is inhabited by literally millions of smaller bodies, each one bearing a part of the story of solar system formation. Where are they? What are they made of? And what remains to be discovered? Mostly we'll be talking about where in the solar system small worlds can orbit without being flung into the sun or out of the solar system by the gravity of larger planets. But let's start by talking about something quite different. Small worlds that are just visiting. They are not gravitationally bound to our sun. We can tell that they're just visiting by characteristics of their path. The orbital eccentricity is a number that measures the amount by which the orbit, the oval of the orbit, the ellipse, deviates from a perfect circle. A value of 0 is a circular orbit. And you can see there in the picture, an eccentricity of 0.7 is a nice ellipse. A value of 1 makes a parabola, which is the borderline case between an elliptical orbit that's closed and repeating, where the body comes back over and over again, and a hyperbolic orbit like the blue one, where the body escapes and does not repeat. As of today, only 2 objects have been discovered with an eccentricity significantly greater than 1. One was Oumuamua, and the second one was something called Borisov. Both of them have this orbital, this trajectory data that indicates an origin outside the solar system. These are the first 2 visiting objects ever observed. And we're going to see more and more of them in the future, since now we're so much better at observations. So now let's turn to resident small worlds, the ones starting that stay in our solar system, at least for now. And we're going to start with the inner solar system. Small worlds are concentrated in areas where they're relatively protected from disruptive gravitational interactions from other objects. Otherwise, of course, they would be moved out of the orbits that they're in. The most familiar of these concentrations of our small worlds is the asteroid belt between Mars and Jupiter. And that's what you're seeing here, just the 4 inner solar system planets and the asteroid belt where it lies outside of Mars. The asteroid belt contains about 2 million objects, but there are an additional 18,000 objects that orbit even closer to the Earth. These near-Earth objects are categorized according to which of the planet's orbits their own orbits cross. So let me show you what I mean by that. Here are the categories of near-Earth objects, or NEOs, all with respect to the Earth's orbit. Each of these categories is named after one of the asteroids in one of these kinds of orbits. The NEO's orbits can be entirely inside or entirely outside Earth's, that is the top and the bottom images here, or they can be Earth crossers, and those are the ones that are dangerous to us. It is a crowded inner solar system. Almost 25,000 near-Earth objects are known. New objects are discovered all the time. 2 new ones were discovered in October, and they're about 20,000 larger than 100 meters. And so here's a picture of the paths, the orbital paths of the near-Earth objects just as of 2014. You can see why tracking near-Earth objects is a major priority for NASA, and especially finding the smaller ones, those under 1 kilometer. We are a bit vulnerable. It's a very busy and crowded inner solar system. So now a public service announcement about asteroids versus comets. And there's our sun there on the left, a star. Small worlds can be made of silicate rock of various compositions that can be made of iron metal, various ices, organic materials, and a wide range of the ratios of these materials has been detected. The most ice-rich bodies. Sometimes are described as dirty ice balls or icy dirt balls. So they're mixtures of things. The rocky material that formed in the inner solar system is usually lacking ices, but there are examples of icy bodies in the asteroid belt, such as the giant Ceres, the asteroid Ceres. Ceres is the largest body in the asteroid belt with a diameter of about 1,000 kilometers. It's a bit less than the length of California. It's big. Comets, on the other hand, are bodies with enough volatile ices that as they approach the sun in their orbit, the ices are heated into gases, and the gases and the dust are lost to space, streaming out behind the main body to make that tail. These designations are not forever, however. Comets can lose their ices over time, and ice-rich bodies in distant orbits can be perturbed into orbits closer to the sun, and then they can develop tails. So there are several million known small worlds and about 6,000 known comets, that is, bodies that form tails. Now, I think all of us have an idea of what a comet looks like with its tail, and so I thought this was much more interesting to show. This is a short-lived outburst from comet 67P Churyumov-Gerasimenko. This is the comet that the amazing Rosetta mission visited. And these images were captured by the Rosetta mission, and they go in time order. So first there's no jet, then suddenly there's a big jet, and then there's no jet. And so as missions go and take pictures of the surfaces of comets, we begin to understand what these sort of armored surfaces are like and what happens when gases break through and form jets. If you have not obsessively looked at all the images and videos from the Rosetta mission, you absolutely should. One that I decided not to show today is a video. It's been sped up quite a lot, so it looks familiar to us, but it's a video of flakes of ice falling down onto the surface of the comet. It's actually snowing on the comet. It's quite amazing. And here is beautiful Ceres, the largest asteroid in the asteroid belt. It's made of a mixture of rocks and ices, and it was visited by the Dawn mission, a really fantastic mission that took this lovely picture. On the other hand, here's the asteroid Bennu, which is a near-Earth object that was just sampled by the OSIRIS-REx mission. They actually put a foot down onto the body, and they jetted nitrogen gas and caused pebbles to scoop up into that foot, and then they withdrew it and put a cap on it, and they're bringing it home. Bennu is much more typical of the small rocky bodies in the inner solar system. It's a primitive asteroid, one that never melted and differentiated into a metal core and a rocky exterior. It's just that primitive material from the beginning of the solar system. And it's about 860 feet across. It's quite small and such an interesting shape. It's just a fascinating, fascinating body and probably pretty typical. Then here are radar images, or really the overlaying of many radar images of two M-type asteroids. Asteroids in the main belt are named according to type with a letter designation, which it turns out has something to do with their composition. These M-types have relatively featureless spectra. That is, the light that reflects off them doesn't have big jags in it, meaning that they're either primarily made of metal or other materials that do not give distinctive features to their reflected light. Psyche on the left is the largest of the M-type asteroids, and Cleopatra on the right is the next largest, shaped like a dumbbell. There are fewer than 10 additional M-types, and they're all much, much smaller. And of course, I can't resist talking a little bit about my favorite space mission, Psyche. Psyche is both the name of our mission and the name of our target, that asteroid Psyche we just looked at. Psyche was discovered and named in 1852 by the astronomer Annibale de Gasparis in Naples, Italy. And Psyche orbits in the outer main asteroid belt between Mars and Jupiter. And as we love to say about this mission, we humans have visited rocky and icy and gas-rich bodies, but we have never visited a metallic body. And we believe Psyche to be largely made of metal. We think it contains the remnants of a metal core of a planetesimal that has been broken by subsequent impacts. It's important to stress, though, that we do not really know what Psyche is. The data makes it very interesting, and we'll find out when we get there. Space always surprises us. So this is what our spacecraft will look like. It's being built right this minute as we speak. And so though I showed you a cool artist interpretation of Psyche in the last slide, this is in fact what Psyche looks like from Earth. It's a tiny dim dot. This is Psyche in that little dot. We do not have any photographs of it, and we do not know what its surface looks like. The best images we have are those radar images that I showed a couple of slides ago. So this is going to be a big adventure. We're going to go see something that no human has ever seen before. And as asteroids go, Psyche is big. It's about the size of the state of Massachusetts. Its diameter is around 225 kilometers. So there it is relative to Los Angeles and San Diego, or Flagstaff and Phoenix, or the state of Massachusetts. Here's a schematic of the beautiful Psyche spacecraft, about the size of a tennis court, and it's being built as we speak, as I said. And just this week, on November 3rd, our industry partner Maxar turned the power on to the spacecraft chassis for the first time in test. This robotic spacecraft will carry imagers and magnetometers and a gamma ray and neutron spectrometer, which will tell us the composition of Psyche's surface. And we'll launch our robotic spacecraft in August of 2022 on a SpaceX Falcon Heavy rocket that will look like this. And we'll cruise out to Psyche over 3 years, arriving in 2026. The mission is just orbiting. It's not landing, it's not sample return, but the spacecraft will orbit the asteroid for 21 months, and we'll learn all about a new kind of small world. So we hope you'll follow along. And you'll be seeing the images of the surface just about the same time we do. We're going to put them out on the internet for everyone to see. Now let's look at small bodies in the outer solar system, from Jupiter to further out. Here you can see at the top part of the earlier image from the solar system, the inner solar system, with the pale blue Kuiper belt, a pale blue asteroid belt at the top. Now you can see with those dashed lines how it fits into the outer solar system, right inside the orbit of Jupiter. And you can see how small our inner solar system really is. The next big population of small worlds is the Kuiper belt. Pluto is a Kuiper belt object. There are hundreds of thousands of objects in the Kuiper belt that are between 100 and 500 kilometers in diameter, it's estimated, but their total mass is not more than 10% of the Earth. It's not that much material in the end, it's just high numbers, but over a huge, huge space. The next, let's see, these outer solar system bodies, particularly those in the Kuiper belt, appear to have surfaces consisting of different ices, including water and methane and ammonia, and carbon monoxide, and others. And they probably have silicate rock particles and also organic materials mixed in as well. But similarly to the inner solar system, there are small bodies that orbit throughout this region. There are centaurs that orbit throughout the region between Jupiter and Neptune, although they're unstable because of constant gravitational interactions with these big planets. Eventually, they'll be moved out of those orbits and sent either further in or further out in the solar system. But then there are special populations of small worlds that are co-orbital with Jupiter. These are called Trojans, and they exist in special stable areas called Lagrange points. So let's talk about Lagrange points. This is a public service announcement on Lagrange points. Lagrange points are positions in space where the gravitational forces of a two-body system, like the Sun and the Earth, here shown in French appropriately, since this was developed by Mr. Lagrange, and they produce regions of enhanced stability because of balancing between their gravitational pulls. There are 5 special points where a small mass can orbit in a constant pattern with 2 larger masses. Of the 5 Lagrange points, there are 3 unstable ones and 2 stable ones. The unstable Lagrange points, labeled L1, there in the picture, L2 and L3, lie along the line that connects the 2 large masses. The stable Lagrange points, labeled L4 and L5, form the apices of 2 equilateral triangles that have the large masses at their vertices. The L4 and L5 points are home to stable orbits as long as, this is interesting, the mass between the ratio between the 2 large masses exceeds 24.96. And so as long as the ratio of those 2 is larger, then L4 and L5 are stable. These conditions for stability are satisfied both in the Earth-Sun and Earth-Moon systems, and for many other pairs of bodies in the solar system, particularly the Jupiter-Sun system. So here's the Jupiter-Sun system being shown. In the solar system, most known Trojans share Jupiter's orbit. They're divided into those that are named after the Greeks that orbit ahead of Jupiter at L4, and those that are named after the Trojans and the Greeks being the warring parties, trailing Jupiter in L5. If you look in the orange ovals that I've drawn, you'll see many little yellow dots, which are the known Trojans. More than 7,000 are currently cataloged, and more than 1 million over a kilometer in size are thought to exist. So those are very highly populated areas for small bodies in the solar system. Psyche's sister mission, Lucy, which is launching next year, is going to visit the Trojans for the very first time of any space mission. And so that's another first for humankind. We're going to go see what kind of objects live and these Lagrange points. In other planetary orbits, we found only 9 Mars Trojans, about 28 Neptune Trojans, 2 Uranus Trojans, and a couple of temporary Earth Trojans even, and a temporary Venus Trojan. I had this idea that we should send a mission to our L4 and L5 around Earth to see what had gathered there. But if there are things that are there more permanently, they're very small. And I also need to mention the wonderful New Horizons mission because it bridges us to the outermost solar system. New Horizons showed us how amazing Pluto really is. And look how far all of this is. New Horizons passed by Jupiter in 2007, and it didn't reach Pluto for another 8 years. And now the spacecraft is continuing on through the Kuiper belt, looking at new objects as it's able. And KBO, by the way, in this picture stands for Kuiper belt object. So here is beautiful Pluto, still alive, that is still losing heat from its interior, heat that drives geologic processes on its surface. Such an amazing small world this is. Pluto has mountains that are made of water ice, which you see here in the red, covered with some organics, frosted with methane snow. And its plains are masses of solid but convecting, that is moving over time in plumes, methane, nitrogen, and carbon monoxide ices. And so in the conditions at which Pluto exists, water ice is as hard as rock is for us here on Earth, and methane, nitrogen, and carbon monoxide are softer ices, and they can actually move over time as they transport heat from the interior. Absolutely amazing. After flying by Pluto in 2015, New Horizons managed to fly by the Kuiper belt object that's now known as Arrokoth. It's a Native American term meaning sky in the Powhatan Algonquin language. It's what's called a contact binary, where 2 icy objects collided gently, they bumped and they welded together. It's only about 36 kilometers long, it's very small. Its spectra, the light reflected from its surface, indicates it's made of methanol, which is CH3OH, hydrogen cyanide, water ice, and organic compounds. And it's now thought that a lot of Kuiper belt objects are contact binaries. So what is out beyond the Kuiper belt? A structure called the Oort Cloud, also made of small worlds. So here we are fitting the whole outer solar system, which you see at the top. You can see Jupiter in the middle and the Kuiper belt at the outside, fitting that whole outer solar system into the middle of a huge structure that's at least 1,000 times bigger, this big structure called the Oort Cloud. Now, what is the Oort Cloud? Jan Oort first proposed this structure to explain the trajectories of long period comets. We have short period comets that return on periods of less than 200 years, and most of them have orbits that lie in the same plane as the orbits of the planets. These comets probably come from the Kuiper belt. But long period comets have orbital planes oriented in many directions, and they have orbits that bring them back on periods of many hundreds to even tens of thousands of years. The average semi-major axis, that is the longer axis of their elliptical orbits of new comets from these great distances, is 22,000 astronomical units. So that's 22,000 times farther from the sun than we are. The Oort Cloud begins at about between 2,000 and 5,000 astronomical units. People are still wondering quite where it is. And it goes all the way out to 50,000 astronomical units. Estimates vary. This is so huge that it's outside of the heliosphere, that is the region of solar wind. So why do long period comets come in from the Oort Cloud? Why don't they just stay happily orbiting out in the Oort Cloud? At those distances, gravitational perturbations from passing stars can give them as much of a push as their gravitational binding to our own star. But half of the mass that's out there perturbing our Oort Cloud is from stars, but the rest is from brown dwarfs and gas and maybe even dark matter. Theory says the Oort Cloud can't get much larger than what it is because of galactic tides, which keep its edges tidy. It keeps shearing off material from the outside. This figure gives you some idea of the sizes of the objects we're talking about. Starting on the left is the planet Mercury, Earth's moon, and then if you keep counting in Eris, and then Pluto, Haumea, this body called Makemake, those are all Kuiper belt objects. The one in yellow, Sedna, is not. It's from further out than the Kuiper belt, and that's what we'll talk about, or yeah, in a moment. Then Charon, Quaoar, and Orcus, all from the Kuiper belt. Ceres, the largest asteroid in the main belt. Varuna is a Kuiper belt object. Then there's Psyche, there for size, my favorite asteroid, and little tiny Arrokoth that was just visited in the Kuiper belt. So that gives you a sense of the size of things. The Oort Cloud objects seem to be too small and too distant to be able to see even with our best telescopes. A few groups around the world, particularly the team of Scott Shepard at Carnegie Institution for Science and Chad Trujillo at Northern Arizona University together, and then Mike Brown and his team at Caltech, they spent a great deal of effort looking for the most distant objects that can be seen in our solar system. Objects out past Neptune and Pluto are small and dim and incredibly hard to detect. And they're all small. The biggest about the size of the asteroid Ceres, and the rest around the size of Psyche are smaller, just 100 to 200 kilometers in diameter. Some of these are called trans-Neptunian objects because their orbits keep them always outside Neptune. And just 3 have been found that are actually trans-Plutonian, always outside Pluto. And the most distant of all so far is 2014 FE72, discovered by Shepard and Trujillo, with the farthest point from its sun of 3,200 astronomical units. This may be actually one of the innermost Oort Cloud objects. Recall that the inner edge of the Oort Cloud is between 2,000 and 5,000 AU. But here's the most amazing thing of all. All these distant bodies, the extreme trans-Newtonian bodies, have their orbits aligned in a particular way. Their orbits are clustered in a way that is beyond the possibility of randomness. They are being influenced by the gravity of a larger object. This object, which seems to be influencing and grouping these orbits, is called Planet 9 or Planet X, depending on who you're talking to. And that's where its orbit has been estimated to lie. This distant planet must have a mass between 5 and 10 times the mass of the Earth. And it must orbit the sun between about 200 and 1,000 AU. And its orbit must be inclined to the plane of the solar system by between 15 and 25 degrees. The characteristics of all the other orbits that are shown in this plot mean that those characteristics must be true of Planet X or Planet 9. We know about how big it is, 5 to 10 times the size of Earth, about how far the inclination of its orbit. So within our lifetimes, we may discover a new planet in our solar system. People are searching avidly. And so our solar system is drenched with small worlds, literally millions of them. The large populations are clustered in the stable regions, the asteroid belt, the Kuiper belt, and the Oort cloud, but they orbit throughout all the planets as well, including some special cases like the Trojans that share Jupiter's orbit. And now the most distant objects we can detect out past the main Kuiper belt indicate the presence of another planet in our solar system. So stay tuned. And thanks so much for coming today.